Have never made an introductory mole video, so here we go. What is the mole? Well, a book will define the mole as a unit for measuring something that you have a whole bunch of. And in chemistry, we typically have a whole bunch of atoms or molecules in a particular sample. But that's not a very real, I mean, it's a realistic definition, but it's not a very relatable one. So, in your life, you have used lots of words that are not necessarily numerical words to stand for numbers. One example is dozen. If you have a dozen of something, then you have 12 of those somethings. Another one is pi. Everybody loves pi. And yes, I'm sure you have pi memorized out to like 20 digits, but who cares? 3.14 is plenty. So this is a word that you have used to stand for a number. Well, the mole is just like that, except it just so happens to stand for a lot bigger number. And for the purposes of our class, if you just want to do 6.02 times 10 to the 23rd, that's fine. That works just fine. And you would use the word mole the same way you would use the word dozen. You could say, I have a dozen donuts, means you have 12 donuts. You could say, I have a mole of donuts, which means you have 6.02 times 10 to the 23rd donuts, which, by the way, would stretch to the moon and back a couple of times, because that's a lot of donuts. So where did this number come from? Well, if you remember, we used the carbon-12 atom to define what an AMU is. Carbon-12 is exactly 1/12 of a carbon-12 atom. Well, 6.02 times 10 to the 23rd comes from the same place, except it's specifically the number of atoms in exactly 12 grams of carbon-12. And sticking with the use of carbon-12 to define both a mole and AMUs, what that means is that all of those atomic masses that are on the periodic table, if it's the mass of one atom, so like if you look, let's say at carbon, carbon on the periodic table has a mass, it says of 12.01. Well, if you're talking about the mass of one atom of carbon, then the units are going to be 12.01 AMUs. If you're talking about a mole of carbon, then the units are going to be grams per mole. And so the fact that they used carbon to define both the AMU and the mole means that those numbers that are on the periodic table can be the mass of both an individual atom and of a mole of atoms. And just in case you're curious, this is what a mole looks like. We have 6 different elements here. We have 4 metals up here, a non-metal and a metalloid. And if you look at these, you go, oh, okay, well, these Petri dishes look to have about the same amount of metals in them. And that's because these metals, there are about the same amount each of them. This is cobalt, this is copper, and this is zinc. And if you look at the periodic table, you see that these guys are all on the same row. They're metals that are, well, I mean, they don't look related, but they are related. And they have relatively the same density. Then you look at this guy and go, well, there's hardly anything in here. Well, this is mercury. And mercury is a lot more dense than these guys. So even though it looks like there's less in here, I can assure you that in all 4 of these Petri dishes, there is 6.02 times 10 to the 23rd atoms of that particular element, whatever the element is. Just FYI, this Petri dish would weigh about half of a pound. A little Petri dish, this little teeny tiny amount of mercury, and you would pick it up and go, wow, that's heavy. And that's because mercury is extremely dense. And then down here we have our non-metal and our metalloid. This, of course, is sulfur. It's a yellow powder. And it looks like there's a lot of it, and that's because sulfur has a very low density. And then this right here, this is arsenic, the widowmaker. Look that up if you don't know what I mean by that. And it looks to be, you know, it appears to be more than the zinc, but it appears to be less than the sulfur, and that's because arsenic, a metalloid, has about a medium density. So we call the mole, the number itself, 6.02 times 10 to the 23rd, we call it Avogadro's number. And this is a picture of the very dashing Mr. Avogadro. And we don't call it Avogadro's number because Amedeo Avogadro came up with the number, but because the work that he did because he did a lot of work with gas chemistry, that work kind of paved the way to discovering this number, and so I guess they decided to just name it after him. So yay him. The nice thing about the mole is that it can be used as a conversion factor between number of things and the mole. And the reason it can be used as a conversion factor is because of this. 1 mole of something is equal to 6.02 times 10 to the 23rd, and I'll go with atoms. It could be molecules, it could be units, it could be donuts, it could be anything. And so because these two things are equal to each other, if you put one over the other, then that means that this would be equal to 1. And you learned very, very early on in your math classes that anything multiplied by 1 is still that same thing. It just might have a different unit with it. And so because of that, we can use this as a conversion factor, and I'll show you how you use it as a conversion factor in just a sec. Okay, you got molar mass. I'm sorry, all my allergies are acting up, so that's why my voice sounds funny, and that's why I'll be coughing some. I'm very, very sorry. All right, molar mass is the mass of 1 mole of pure substance. Chemists weren't real creative in naming that molar mass the mass of 1 mole. And it does have the units of gram per mole, and just like I said earlier, it is the same, numerically speaking, as the average atomic mass that's on the periodic table. It just has different units. And it can also be used as a conversion factor, except instead of between moles and atoms, this is between moles and grams, because if you look at the units, you're relating grams and moles, and so this is how this one works. If you pick an element off the periodic table, let's say you pick nitrogen, and nitrogen, according to the periodic table, has a mass of 14.01 grams. Those of y'all that have a bit of a background in chemistry, you're going, hey, wait a minute, nitrogen is diatomic, it should have a mass of 28.02. I'm not there yet. We're not talking about pure state elements. We're just talking about the elements themselves. And so 14.01 grams of nitrogen is equal to 1 mole of nitrogen. And if you're listening to this going, diatomic, what the heck does diatomic mean? Don't worry about it. It has nothing to do with this right here. If you really need to know diatomic, you can look it up. But we're not talking about diatomics right now. So these two numbers are equal to each other. And we can set up, just as we did with the moles and the atoms, we can set up a statement of equivalence and say 14.01 grams of nitrogen over 1 mole of nitrogen is equal to 1. Just like I said before, anytime you multiply something by 1, you get that same something. You just might have shifted the units a little bit. So what's the point? Whoops, sorry. What's the point? Well, this is how you can know what to use to convert from what to what. So I would suggest writing this down, bolding it in your notes of some kind, just making it stand out so that you can come back to it later. So here are just the rest of this is just example problems. Fast forward to whichever kind of example you need. Write them down, pause me if you need to, just do whatever you need to do to get this taken care of. So when you're doing a gram to mole conversion, you have to use molar mass, and the molar mass you find on the periodic table. So our first example question is, if you had 32.3 grams of sodium, how many moles of sodium do you have? Now I'm going to show you a way to set this up. Yes, you can very easily solve this by using a proportion. However, stoichiometry, that's a big word, I haven't used it before. Conversions, I'll use that word for right now. Conversions can get a little complicated, and you can use a method that's used in stoichiometry, and stoichiometry is just a great big word for chemical conversions. You can use this box method. I love it. It helps keep things very nice and neat and organized. If you don't like it, then don't use it. But I will say that if you watch my videos, the box method is what you will see from me. So to show you how to set this up, you always start with whatever number you were given. So in this case, we were given grams of sodium. And we want to convert to moles of sodium. Well, to get from grams to moles, you use the molar mass. So if you look at the periodic table, you see that sodium has a molar mass of 22.99 grams per mole. Now, in math class, you learned, let's say I were to write this, 4x squared over 8x. Chances are you're so, like the habit is so ingrained in you by your math teacher that you would look at this and know that I'm about to ask you to simplify it. And if you were to simplify this down, you know that the 4 and 8 reduce out. The 4 becomes a 1, the 8 becomes a 2. And then with the x squared and x, you're going, okay, well, x squared, you take 2 minus this imaginary 1, and you just get x. Well, for our purposes, it might be easier to illustrate it like this. Instead of x squared, let's write x times x. And you can see that we've got an x on top and an x on bottom, so they cancel each other out. And then what you have left is x over 2. You just simplified this down to its simplest form. Well, we're going to do the same thing over here in order to get rid of grams and convert into moles. And so I'm going to use this conversion factor to do it. Now, this horizontal line right here, it means the same thing as this horizontal line right here. It means divide. And if a horizontal line means divide, well, why can't a vertical line mean multiply? And so I'm going to put this, I'm going to insert it into here in such a way that my grams will cancel out. Well, since I have grams above the line here, then I want my grams to go below the line. And the reason that it's okay that I flip this conversion factor is because it doesn't matter which of these is on top. These two things are equal to each other. So either one of them can be on top, either one of them can be on bottom. So since my 22.99 grams went on bottom, I need to put my 1 mole on top. And since I have grams of sodium on top and grams of sodium on bottom, they simplify out. And now I can just simply do my math. And you can look at this and go, okay, 32.3 times 1 divided by 22.99, you plug that into your calculator, and incorrect sig figs, you're only allowed 3 sig figs, you get 1.40 moles of sodium. Now some of you are probably going, well, hey, what about this little area right here? Don't I need to put anything right there? No, this just stays empty. Your first box, I call each of these boxes, will have something only in the top, not in the bottom. Your next boxes will always contain conversion factors. Conversion factors are the only things that can go in these next boxes. So let's do one more example, shall we? If you have 0.56 moles of iron, how many grams of iron do you have? Well, so now we're starting in moles. So I'm going to write that out, 0.56 moles of iron. Draw my horizontal line. And I know if I'm dealing with moles and grams that I'm dealing with the molar mass, so I'm going to look at my periodic table, and iron has a mass of 55.85 grams per mole. So I'm going to take this conversion factor and I'm going to put it in right here. So since I have moles on top, I know that I want to have moles on bottom. So for every mole of iron, I have 55.85 grams of iron. Another way to remember, what units go where, whatever you have here, you're going to put that same unit in the caddy corner of the next box, or in the bottom of the next box. And I almost always fill in the bottom and then I fill in the top. So I'll fill in my boxes like this, and that's just so that I don't get lost. And so you can look at this and go, okay, moles of iron cancel, and I have to take 0.56 and multiply it by 55.85. All that I have left on the bottom is 1, and anything divided by 1 is just that something. And so this works out to incorrect sig figs, we're only allowed 2 sig figs, 31 grams of iron. Move on to our next type of problem, converting from number of atoms to moles. We're going to use Avogadro's number, so just to refresh your memory on what that is, it's 6.02 times 10 to the 23rd atoms per mole. Oh, FYI, this is the abbreviation for mole. You just simply drop the E. Seems kind of silly, but it is what it is. Again, sorry about the coughing. So if I had 1.40 moles of sodium, how many atoms do I have? So I'm going to draw my line. Draw my vertical line. This just separates my conversion factors. You could use parentheses on this. You could separate them with the times, with the little X standing for times, whatever. I just like the organizational aspect of this. So I'm trying to convert from moles to atoms, which means I'm going to use this conversion factor right here. Well, whatever I have in the top in my first box, I want down in the bottom of my next box. So that means this mole, 1 mole of sodium goes in the bottom, and my 6.02 goes in the top. Cancel out my moles. What I'm left with is atoms of sodium, which is what I want to be in. And so you can see all I have to do is multiply 1.4 times 8.02, and you end up with, it was 8 point something, 8.3 something. I guess I'll actually have to enter this in because I don't remember what it is. 1.4 times 6.02 E23, 8.43. So it's 8.43 times 10 to the 23rd, and the units are atoms of sodium. And the next one, if we have 3.43 times 10 to 23 atoms of iron, how many moles do we have? So now we're starting in atoms and going to moles. Same setup, write what you know, draw your line. But this time we are starting with atoms, so that means atoms needs to be down here in the bottom. So we're actually going to take this conversion factor and flip it and put my 6.02 times 10 to the 23rd atoms on bottom and my 1 mole on top. And so my atoms cancel. I'm left with moles of iron, which matches the units that I want to be in. And you can see I'll take 3.4 times 10 to the 23rd times 1, which is just this number, divided by the 6.02 times 10 to the 23rd. And because I only have 2 sig figs, my final answer can only have 2 sig figs, and my final answer is 0.56 moles of iron. One type of problem left, and that's the combo problem. If you go back to the little thing that I gave you here, you can't go directly from grams to number of atoms or from number of atoms to grams. There isn't a connection there. But what you can do is go from grams to moles and then moles to atoms, or go from atoms to moles and then moles to grams. Either way, you have to go through the mole, which is a lot of times why the mole is known as the heart of chemistry, because a lot of your calculations are going to have to go through it, just like the blood in your body has to go through your heart. So whenever you have a conversion of grams to atoms, you're going to have a 1-2 step problem. You'll have to use both molar mass and Avogadro's number. So let's go back to that slide and work those out. So the first question we have, if you have 0.0326 grams of nitrogen, how many atoms of nitrogen is that? So 0.0326 grams of nitrogen, that's the number we were given, so that's where we're going to start. Well, the first thing that we're going to need to do, we're in grams. Grams is our starting unit. Well, we got to get to moles. So to get to moles, you use the molar mass. And if you look at the periodic table, you'll see that nitrogen has a mass of 14.01 grams per mole. And because I have grams on top, I want my grams to be on bottom. So 14.01 grams of nitrogen are contained in every 1 mole. Now my grams of nitrogen cancel and I'm in moles, but that does not match the units that I want to be in, so I know I need another step. And this is where Avogadro's number is going to come in. 6.02 times 10 to the 23rd over 1 mole. Now I've got moles on top, so that means I need my moles to be on bottom over here, so they'll cancel out. So 1 mole of nitrogen will have 6.02 times 10 to the 23rd atoms. Draw my line a little longer. And now my moles cancel out. And I have atoms, which matches what I want to be in, so that means I'm done. Yay! And if you look at this mathematically, you'll take multiply across the top and then divide by what's on the bottom. So you'll take 0.0326, divide it by, or I'm sorry, multiply it by 6.02 times 10 to the 23rd, and then divide that by 14.01, and when you plug that in, you end up with, oh, I'm forgetting again, where's my calculator? Oops, there. 0.0326 times 6.02 times 10 to the 23 divided by 14.01, and you end up with 1.40 times 10 to the 21 atoms of nitrogen. And again, 3 sig figs because this number has 3 sig figs. I guess I could have just done that to get the answer, couldn't I? Okay, last one. I think I have time to knock this thing out. If the bell rings in between or while I'm working this out, I'm sorry. I'll work this one out as quick as I can so we don't get that obnoxious bell in this video. So now we're starting with atoms. 2.01 times 10 to the 41 atoms. That's a lot of atoms of hydrogen. And we want to know how many grams is that. Well, starting with atoms means that we have to start with Avogadro's number. Since we have atoms here, we want atoms to be in the bottom of the next box. So the 6.02 times 10 to the 23rd atoms goes there. And 1 mole goes on top. Well, atoms cancel, and now I'm in moles. I don't want to be in moles. I want to be in grams. So one more step. Moles is on top, so moles goes on bottom over here. 1 mole of hydrogen, look on the periodic table, has a mass of 1.01 grams. And plug that into your calculator, and you get 3.37 times 10 to the 17 grams. That's a lot of freaking hydrogen. If you have any questions, just let me know. And if not, have a great fair day tomorrow, and I will see y'all when we get back. Ooh, that's a lot.